Good morning, everyone. I'm Javier, PhD student here at CRCT. Today, I'm going to present my work on the creation of an intermetallic database for heat-treatable alloys and some of our new work on the calculation of thermodynamic properties. This is a work done with the collaboration of Ayman Geribi, Paul Lafay, Rodrigo Wang, and Jean-Philippe Harvey. So I'm going to start putting this project in context. Material design is a key strategy in the aluminum industry where, for a given set of target properties and the right models, it gives way to the creation of functional materials. Here, it's of great importance to have a good and accurate understanding of the thermodynamics of materials. That's why me and our team are working on the development of the next generation thermodynamic database, where experimental data is complemented with atomistic simulations for compounds and solutions, modeling stable but also metastable phases for a precise description of the Gibbs free energy. We know that for heat treatment, we dissolve the alloying elements heating slightly above the solvents, and then, during quenching, metastable phases will form and make way for the precipitation of equilibrium phases by aging. This will determine the final microstructure and therefore the physical properties of the alloy. It is important then that we consider not only the stable phases but also the metastable ones in order to have a proper description. The problem for metastable phases and Kalfat approaches is that you need data, which is hard to find experimentally for metastable phases. So, in order to complement data that exist and thus have a complete description of those intermetallic of interest, we need to use numerical calorimetry. I'm going to say a few words about the system we are studying. Within the subject of material design, we would like to have the L12 phase forming. The problem is that in aluminum alloys, scandium is the only element that forms a stable L12 phase. However, these other elements form the 022 and the 023 phases that can be transformed to L12 by alloying with other elements like these ones here. Then, in the context of this project, our objectives are to fill the gap of data that exists for metastable D022, D023, and L12 phases of the compound Al3X, where the X are the elements here listed, to finally apply this to the computation of accurate solubility limit. For industrial applications, it is of relevance to have an accurate description of the phase stability. This is done by computing at each temperature the Gibbs free energy as a function of composition. This Gibbs energy and its different contributions can be obtained by using different methods. There are several models that describe the internal energy, some of them more suited than others for this kind of metallic systems, like the tight binding in the second moment approximation. Some others can incorporate explicitly the internal crystalline structure, like the most potential. For the vibrational part, which is a big contributor to the free energy, it can be computed using the quasi-harmonic approximation, the Debye-approximation approximation, or by a new, more accurate and self-consistent approximation that we are now in the process of developing. You have to note that a little deviation on the Gibbs energy of a phase could lead to huge errors in the prediction of the solvents. For example, a couple of hundred of joules could cause problems when determining the phase stability. That's why it's so important to have an accurate description. The new approach for the vibrational contribution is an extension of the Debye approximation. It is formulated in such a way that all thermodynamic properties are derived directly from the free energy without losing self-consistency. So no self-consistent loop are required, no empiric approximation to the heat capacity or the Grunizing parameter are used, and one interesting property it also has is that a description of the intrinsic anharmonicity can also be included. Also, it's a very fast and simple way to calculate accurate thermodynamic properties that can be integrated later with factsheets to complement what's already there. Here are some results of the application of this methodology. These are results for the heat capacity and thermal expansion I calculated for elements and compounds. Elements are compared with experimental data with reasonable accuracy. For the compounds, there are no experimental data available. This is being integrated into a factsheet database for heat-treatable aluminum alloys. I mentioned that all thermodynamic properties are obtained from the free energy. Here, the internal energy plays an important part. We are working on extending the methodology to take into account the atom positions and the internal interaction inside the structure to describe the energetic of compounds. We have implemented the Morse potential that uses internal structure information to calculate the internal energy. This information can be calculated for a given structure through a pair analysis. We are working now in the prediction of the internal energy of compounds by training the unary and binary interaction to be able to perform calculations fast and without the need of complex calculation like density functional theory. As it was previously mentioned, we have implemented a set of tools that will allow us to generate structures, run pair analysis, and also predict thermodynamic properties. This was already implemented, and now we can calculate reasonable accurate thermodynamic properties for unary systems and binaries, but also we can now predict the heat capacity for compounds without using density functional theory, which is a huge improvement to our methodology, since now we no longer require extensive time-consuming calculations to have equally accurate results. This concludes this presentation about our work in the computational thermodynamic representation for heat-treatable aluminum alloys. Thank you very much.